Our next concept is the addition to an alpha beta unsaturated aldehyde or ketone. This is called conjugate addition, and it should look a lot like addition to conjugated alkenes when we were looking at 1,2 and 1,4 addition back at the beginning of Organic 2. So the idea here is that after an aldol condensation, you have an alpha beta unsaturated carbonyl compound. Notice that these two pi bonds are conjugated. So when a nucleophile comes along, there are two different places that the nucleophile could attack. It could want to attack the carbonyl compound, which would give us the straightforward so-called simple addition. This is analogous to 1,2 addition to a conjugated alkene, or it could attack in the beta position, and this is called conjugate addition. This is analogous to 1,4 addition, kind of, but notice you end up with a hydrogen in the 3 position and nucleophile in the 4 position. It's this here that is analogous to the 1,4 addition. But of course, an enol would tautomerize to the keto form. So strong nucleophiles tend to go through simple addition. They are highly reactive. They do not want to worry about trying to create the more stable product. They are going to just attack the carbonyl compound and get it over with. Whereas your weaker nucleophiles are going to go through conjugate addition because they're going to go through this stabilized 1,4 addition type product and then tautomerize to the keto form. So again, recall your 1,2 and 1,4 addition to alkenes. The alpha beta unsaturated carbonyl compound has a couple of resonance forms. So first, you can move the electrons from the carbonyl pi bond up onto the oxygen, and that's going to give you resonance form B. And then resonance form B is stabilized by moving the pi electrons from the alkene towards the carbocation to create a new alkene. This shows you why that beta carbon is electrophilic. It's because you have this stabilizing resonance form here. So simple versus conjugate addition. As long as you kind of follow the rules, it's actually not too difficult. So in this first reaction, we're looking at an alpha beta unsaturated ketone, and we're adding in a Grignard. Grignards are very strong nucleophiles, and so they're going to tend to attack the carbonyl carbon, and you're going to see very little of the conjugate addition product. But if you add in a weak nucleophile, such as cyanide, which is a good nucleophile but a weaker base, and therefore a weaker nucleophile than a Grignard, you're going to end up with mostly conjugate addition. So it's largely going to attack in the beta position. So this is going to be weak nucleophiles including cyanide, enolates, and amines. They are all going to add in the beta position. This brings us to the Michael addition, which is the conjugate addition of an enolate. So when you add an enolate into a reaction mixture containing an alpha beta unsaturated carbonyl compound, that enolate is going to add to the beta carbon of the alpha beta unsaturated carbonyl, which forms a new carbon-carbon bond. And this is eventually going to tautomerize to the keto form, and this is what's called the Michael addition product. There's a lot of variety in what can be done with a Michael addition. So that variety is largely dependent on what can be considered a conjugated system. So an alkyne in the alpha beta position to a carbonyl is considered a conjugate system. And then you can also have an alkene next to a nitrile, any combinations like these. Notice this is an ester and not an aldehyde or a ketone. That variety is going to mean that Michael additions can look very different depending on your starting material. So if we add in acetoacetic ester in the presence of ethoxide, we know that that's going to give us an enolate here, which would then attack the nitrile. And that's going to push pi electrons onto the alpha carbon. That looks like this, which will then be protonated by ethanol. Whoops. To give us our final product. The mechanism for the second problem is very similar. Diethylmalonate can be deprotonated easily to create an enolate. You would attack the conjugate, the beta position of the nitrile. That pushes the electrons onto the alpha carbon, and then they would be protonated to form our product. You can also do a really cool combination Michael addition and Stork enamine reaction. So remember that in a Stork enamine reaction, you're using an enamine essentially as an enolate. So if you take these electrons, bring them down and create a pi bond, that's going to push out these pi electrons to attack the beta carbon, because it's going to be a weak nucleophile, which would push those electrons onto the carbon alpha to the nitrile. And then this can be protonated by the ethanol that's in the mixture here. And then through the addition of water, we would end up hydrolyzing this aminium ion and getting back our ketone. Our next reaction is the Robinson annulation, which is a Michael addition followed by an aldol condensation to build one ring onto another. So in this example, you have this beta dicarbonyl compound, which means this hydrogen is the most acidic hydrogen in the reaction mixture. So it doesn't matter that there's also an alpha hydrogen on the methyl vinyl ketone. So we'll form the enolate out of the 2-methyl cyclohexane 1,3-dione, which will then, by conjugate addition, add to create the compound here in the middle. So here's the bond that was made through that reaction step. And remember, we've added on a hydrogen here during the Michael addition. And then in this final step here, we now have a situation where there is an alpha hydrogen on the methyl carbon that will be pulled off, turned into an enolate, so that a 6-membered ring can be formed through condensation. So imagine forming the enolate here, which attacks that carbonyl.